Hello everyone, welcome to today's presentation on titanium alloys. Titanium's discovery dates back to 1790 and it was further purified in the early 1900s. Initially, it took time to find its place, but in the second half of the 20th century, titanium emerged as a material of unparalleled significance. Our discussion will examine structural properties, mechanical properties, strengthening mechanisms, and diverse applications. In this presentation, we'll delve into one of the 5 classifications of titanium alloys, namely alpha-beta titanium alloys. In alpha-beta titanium alloys, we need to understand the crystallographic attributes of both the alpha and beta phases. There are 2 known crystal structures of titanium, A. closed pack hexagonal or the alpha phase, and B. the body-centered cubic or the beta phase. A crucial stage in the transformation process of titanium alloys is the rapid or gradual cooling from the high temperature beta phase fusion. In this operation, the beta phase changes into the alpha phase. Additions of alloying elements to pure titanium produce the range of possible microstructures in the titanium alloys. Alloying elements are classified as alpha stabilizers, beta stabilizers, and neutral additions in titanium. With sufficient addition of beta favoring alloying elements, beta phase is produced. On heating alpha phase to beta transits, followed by the phase transformation during cooling and the high processing, leads to formation of alpha beta alloys. In this slide, we can observe the preferred slip planes and dimensional parameters. HCP structures offer 3 slip systems, while BCC structures provide 12, making BCC more favorable for dislocation movements. Highly packed atom planes and directions promote plastic deformation with greater ease. Slip planes with tightly packed atoms facilitate smoother dislocation gliding. Therefore, slip planes in HCP lattices being more closely packed seem preferable over BCC's 83% packing density. However, the energy required for plastic deformation depends on the length of the minimal slip path. The minimum slip path in BCC is less in comparison to HCP structures. As a result, BCC's plastic deformation is preferred over HCP structures. There are 5 different microstructures we observe in alpha-beta titanium alloys. In fully laminar microstructures, we have layered arrangement of alternating alpha-beta phases, forming thin parallel plates across the alloy. To control the beta grain size, recrystallization temperature is maintained at 30 to 50 degrees Celsius above the beta transits. The standard beta grain size is usually around 600 micrometers. In Widmann-Staten structures, the primary beta grains are coarse and extensive. On the grain boundary, continuous alpha particles grow. In the figure, the alpha lamellar colonies are dense, dark, and parallel. Slow cooling rates on the beta phase zone reveals Widmann-Staten structure, which has low ductility and strong fatigue performance. Bimodal or the duplex microstructures. The modified beta matrix contains slightly more or less than 50% of discontinuous equiaxed alpha particles. When an alloy is deformed or heated in the upper portion of the alpha plus beta phase zone, a duplex structure with comprehensive mechanical properties is formed. The basket weave structure. In the basket weave microstructure, the primary beta grain boundaries are obliterated and alpha lamellar across various orientations become shorter. This enhanced ductility structure forms when substantial deformation occurs near the beta transit temperature. In the equiaxed structure, over half of the primary alpha grains and some modified beta grains exhibit irregular polygon shapes. Unlike the elongated needle-like grains in Widmann-Staten structure, equiaxed structure have more symmetrical and randomly distributed grain shapes. Cooling effect. Cooling rate of the beta phase is crucial as it determines the key features of lamellar microstructures, including the size of alpha lamellae, the width of grain boundaries, alpha layers, and alpha colonies. As shown in the figure, higher cooling rates lead to reduction in the size of alpha colonies, width of the beta grain boundaries, and alpha layers. We will now discuss the mechanical properties and basic comparison between the lamellar and bimodal microstructures of alpha-beta titanium alloys. Yield stress and ductility in the lamellar microstructures of the titanium alloys are influenced by the cooling rates from the beta heat treatment temperature, which in turn affects the size of the alpha colonies in the alloy. Faster cooling rates lead to smaller slip lengths in the alloy, resulting in higher peak values of yield stress for different alloy compositions. Additionally, higher cooling rates produce fine microstructures in the alloy, further enhancing the yield stress. Conversely, ductility and percentage elongation reach their peak at moderate cooling rates but sharply drop off at high cooling rates due to the increased yield stress associated with the reduced slip lengths. The beta grain size plays a crucial role in the mechanical properties of bimodal microstructures. This size is determined by the volume percentage of primary alpha phase grains in the alloys, which in turn is influenced by the beta cooling rate during the alpha beta processing. The yield stress demonstrates a peak value at approximately 10 to 20 volume percent of alpha phase. However, increasing colony size leads to a decrease in the yield strengths due to the negative impact of alloying elements. Remarkably, bimodal structures exhibit higher ductility compared to the lamellar structures. The bimodal structure exhibits a slower microcrack propagation rate than the lamellar structures. Conversely, the macrocrack propagation curves shows the opposite trend, attributed to the significantly rougher crack front profile in the lamellar structures compared to the bimodal form. An increased alpha phase volume fraction typically leads to reduced high cycle fatigue strength. In the bimodal structure, fatigue cracks originate in the lamellar grains, which are softer than the alpha phase due to the alloy element partitioning effects. In lamellar microstructures, evidently, coarse microstructures exhibit higher fracture toughness compared to bimodal ones. Fracture properties are ascertained by alpha colony size rather than differences in yielding behavior. The bimodal microstructure of Ti6Al4V alloy demonstrates a fracture toughness of approximately 55 MPa under root meter, which is significantly lower than the toughness of coarse lamellar structure. This observation aligns with the relatively smooth crack front profile of the bimodal microstructure. Creep resistance. For high temperature application, creep resistance is a very important property in addition to fatigue resistance. It can be seen that fully lamellar microstructures exhibit better creep resistance than bimodal microstructures. This decrease in creep resistance of the bimodal microstructures with increasing volume fraction of alpha phase over the whole range of cooling rates is shown in the figure. This can be explained by the negative impact of alloy partitioning effect in the bimodal microstructures. Strengthening mechanisms. The strategy for strengthening metals involves three approaches. Firstly, composition design, which considers the chemistry of a metal or an alloy to achieve the desired microstructure. Second, the processing methods, that includes casting techniques, which plays a major role in strengthening. And finally, post-heat treatment processes such as aging and precipitation hardening, which are used to achieve the desired strength. For alpha alloys, as titanium is highly unstable and tends to make oxides, it is extracted in the presence of a vacuum or a noble gas. During this extraction, the inclusion of interstitial or substitution elements increases the strength by restricting the movement of dislocations. While recrystallization, the titanium aluminide is precipitated, making it brittle in nature. These small brittle regions increase the overall strength. For alpha plus beta alloys, it was seen that alpha phase starts getting precipitated in the form of disc or plate around the beta phase boundary layer, which on annealing at low temperatures at various cooling rate give different microstructures. These subsequent regions of primary and secondary alpha phase regions in the beta phase hinder the movement of dislocations and hence increase the strength of the alloys. Processing titanium at high temperatures can result in various types of alpha and beta matrices, leading to fully lamellar, fully equiaxed, or bimodal microstructures. Remarkably, the bimodal microstructure demonstrates exceptional strength when grain size is refined to nanoscale, creating numerous boundary layers that hinder the dislocation movement. In specific applications, different elements are introduced to stabilize titanium or enhance specific properties. For beta alloys, the important parameter to keep in mind while making beta alloys is the recrystallization temperature, which is higher than the previous alloys, and the high cooling rate and high annealing temperature, finally resulting in these structures with the increase in strength. Lastly, processing near the beta transit region and cooling it subsequently at high rate precipitates the alpha platelets into very thin regions by making beta regions stabilize at room temperature. Using beta promoting alloy elements like iron, molybdenum, vanadium, and chromium. And finally, the applications. Alpha beta titanium alloys are widely used in aerospace components like aircraft frames, engine components, landing gear, and fasteners. Their high strength to weight ratio and good corrosion resistance make them ideal for aerospace applications. These alloys are also biocompatible, making them suitable for medical implants such as joint replacements, bone plates, and screws. Their low modulus of elasticity and excellent corrosion resistance promote better integration with the human body. Titanium alloys also find their use in safety critical applications, marine equipment, high performance springs, and the oil and gas industry, just to name a few sectors where they are used.